Okay, here's a nice overview of titrations, all right? And I'm going to try to focus on everything that we've learned, and I'm also going to try to focus you on what you need to know, okay? Because I don't believe that you need to be able to calculate the pH at every point in a titration, but I do think that would be helpful. So let's start with, we'll do a straight regular weak acid, strong base titration. My weak acid will be, for ease, let's do 0.1 molar HF. And my strong base will be 0.1 molar NaOH. Okay? So we're going to start with the first region, which is the initial pH. Okay? So your initial pH is dependent on what's in the beaker. So this is initially at 0 milliliters. So I haven't added any base yet. So the only thing that's happening in my beaker is this equation. Oh, excuse me. HF is turning into H plus and F minus. Okay? The neutralization reaction that happens when we add the base is HF plus. I'm going to do the net ionic equation. Na doesn't matter here, okay? Turns into H2O plus F minus. But I have a certain number of moles, and I'll get there. Let's say I've got 50 milliliters, okay? So I have a certain number of moles of HF. To get the moles of HF, hopefully you can do this, but it's going to be 0.1 times 0.05. And that gives me 0.005. But I have 0 of this, 0 and 0. So they're before and after chart, I have nothing to react. So all that's happening is that my HF is dissociating, but that hits an equilibrium, okay? Your before and after charts are going to be in moles, okay? They should be in moles, and your ice charts need to be in molarity. And that's a fine little difference that ultimately on the AP exam, etc., I don't think it's going to come into play. But as far as your understanding, ideally you would know the difference there. Okay, so my concentration of HF is 0.1. I don't know, I have none of this and none of this. My change is going to be by X plus X plus X. So this is 0.1 minus X. This is X and this is X. You can make the assumption, which I'm going to do for ease and quickness here, that the Ka, which is 6.8 times 10 to the negative fourth, equals X squared over 0.1. I'm going to assume that 0.1 minus X is small enough that it's not going to make a difference. So I'll do 0.1 times my Ka. And I'm just guessing that that's the Ka. I'm just trying to remember, so forgive me if it's wrong. But and then I need to take the square root of that, which I don't know where it is on my calculator. There it is. And I get an X squared of 0.0082 molar. And that's my concentration of H plus. To get my pH, I'm going to take the negative log of that. Oh, I don't have a log key on this, so that's going to be super fun. Okay, so let me do that over here. So I get a pH of 2.1. All right, how would this step, the initial pH, be different? If you have a weak base, you would need to do the Kb. You'd look up the Kb, it'd be right off the table, and you'd calculate the OH minus concentration. And remember, if you do get the OH minus concentration, when you take the negative log of that, it gives you your POH, so you'd have to go to pH from there. If you had a strong acid, strong base, you wouldn't have to do an ice chart. You would just take the negative log of your initial concentration. So that's how the that initial pH, that's how it could vary. Okay. Now, the second part, the second phase is in the buffer region. Okay, so the buffer region, remember, is going to be, this is our weak acid, strong base titration. I've got 50 milliliters of HF, and it's 0.1 molar. There's my 0.1. Okay, so here's my initial, that's where I was. Now my buffer is like from here to here or so. The biggest thing that you have to know is that at half the equivalence point, your pH equals your pKa. So what's my pKa? Well, it's just the negative log of your Ka, which I have to do over here. So 6.8 E4 negative. So I'm going to take the log of that. And my Ka, my pKa is 3.17. All right. So at half my equivalence point, my pKa is 3.17. Well, how do you know where that is? Well, odds are you'll probably have a graph, okay, like this, and you can kind of read where that equivalence point is in terms of volume. Because my concentrations are the same, my equivalence point is going to be 50 milliliters of base. But you could figure that out using this formula, M1V1 equals M2V2. Okay, where this is the molarity of your acid, which in our case is 0.1, and the volume of your acid equals the molarity of your base times the volume of your base, which we would get as 0.05. So our equivalence point is at 50 milliliters. So half of our equivalence point is 25 milliliters. And at 25 milliliters, my pH equals 3.17 because my pH equals my pKa. Now, that's because I've neutralized exactly half, okay? And so it's the same equation that we did before. The HF plus the strong base. This goes to completion because anytime you are adding a strong base or a strong acid, the opposite that's in the buffer is going to neutralize it. So if you're adding a strong base, the acid part of the buffer reacts with it. And if you're adding a strong acid, the base part of the buffer reacts with it to form water and F minus. So if we're doing a before and after chart, I think I said that I've got 0.005 moles of HF. That's not changing. That's always going to be where I start. And I've added at half my equivalence point, half of the moles of OH minus, so 0.0025. And I have 0 and 0 of this. Well, my base is what's limiting. So I have 0.0025, 0.0025, and 0.0025. Nobody cares about water because that doesn't play any part. But when I'm now doing my Henderson-Hasselbalch equation, I can only do the Henderson-Hasselbalch equation here, okay? Or as Sky likes to say, the Hasselhoff maneuver, okay? I can only do that here because this is a buffer, and this is the only part that I actually have a buffer, and you can only use that equation when you have a buffer. That is the pH equals the pKa plus the log of the concentration of your base over the concentration of your acid. Now, in this case, because you're dividing concentrations and it's a 1-for-1 ratio, you can totally use moles in your Henderson-Hasselbalch, but it's better to get in the habit of just always putting it into molarity. So I'm looking for my pH. I already said that my pKa is 3.17 plus the log of the concentration of my base over my acid. Now, that is, to get back to your concentration, we have 0.0025 moles. And divided by the total volume, which at this point, I have the 50 milliliters of my acid, and I've added 25 milliliters of base, so it's over 75 milliliters. I have this in milliliters, and obviously it needs to be in liters, so I'll divide that by 1,000, just for completeness sake. And I get 0.0025 divided by 0.075, and I get that my concentration is 0.033. However, that's my concentration of my acid part, which is here, and my base. So I'm going to get that the concentration of 0.033 over 0.033, and I should get that my pH equals 3.17, which I expected because I said my pH equals my pKa. If for some reason you added less than half of the hydroxide, you would have a little bit more acid and your pH should be a little bit lower. Remember to adjust your volume down here. I'll do that in a different color so you can see it. If you added more than half the base, so like 30 mils or maybe 35 mils, you would be a little bit above the pKa. Okay, you'd be at a higher point here, and your again, your volume would be different, so you'd have a higher number here, so your concentrations would vary. But that's not the main point. It would be that your pH would be a little bit higher. Okay, if you were doing the strong acid, weak base, the only difference again here would be your make sure that you get the pKa, not the pKb, because you would have a higher pH. So you need to calculate the Ka and get the pKa, not the pKb, and you'd have to. That I think would be it. Okay, so remember you're reacting the acid, and then you've got your base over. Still going to be your base over the acid. So the formula should be the same. The equivalence point is probably the hardest calculation. Okay, because there's a lot of moving parts here. But it's really not that hard, so don't let it overwhelm you. At your equivalence point, that's where your moles of acid, this is always true, equal your moles of base. So in this case, we just calculated it on the last slide. In this case, our equivalence point is at 50 milliliters of strong base. So again, we're starting with this equation. This one goes to completion, so it's a single-sided arrow. It forms water and F minus. So this is where my question of what's in the beaker comes into play. I'm starting with 0.005 moles. I'm adding 0.005 moles and 0, 0. This goes 0, 0. So what I have in the beaker is F minus, there we go, and water. Water obviously is not going to affect the pH. Nobody cares about the water. Can the F minus affect the pH? Now, if you're doing a strong acid, strong base titration, everything's strong, then the conjugate base of your acid is not going to affect the pH. It's going to be Cl minus, or it's going to be I minus or Br minus, and we know from chapter 16 that that's not going to affect the pH of the water, of the solution. However, the F minus is, and how does it do that? A hydrolysis reaction. So it's going to do F minus, it's going to react with the water, and this hits an equilibrium, so it's a double-sided arrow, forms HF and OH minus. When I see it forming OH minus, I know that it's not a Ka equation, right? A Ka equation is going to produce H plus. This is going to be a Kb equation. So I have to calculate the Kb of my stuff here. So it's 1 times 10 to the negative 14th divided by my Ka, which is 6.8 times 10 to the negative 8, not 8th, fourth. And I get, I did 48th, that's wrong. Excuse me, there we go. And I get that my Kb is 1.47 times 10 to the negative 11th. And it's helpful to note here, the stronger the acid, the weaker the base, and this is a really, really weak base. And that makes sense because HF is a pretty decent acid. So this is my Kb expression. I have my number of moles of this, but I don't necessarily have my molarity. Remember that your before and after charts, your bar charts are moles, and your ice charts, which are the equilibrium charts, are in molarity. And that is important here, and it is going to matter. So I'm going to take my number of moles of F minus, and I'm going to divide it by the total volume. Well, I started with 50 milliliters, and I'm adding 50 milliliters to get to my equivalence point, which I calculated on the last slide. So I'm doing 0.005 divided by 0.05 plus 0.05, and I get a concentration of 0.05 molar. Okay? So now I put this in concentration, 0.05, nobody cares about water, 0, 0, minus x, plus x, plus x, 0.05 minus x. Again, I'm going to make that assumption Okay, so I get that my KB equals x squared over 0.05. So when I solve for that, I have 1.47 e to the negative 11th. That's my KB times 0.05. And then I'm going to take the square root, which I found. And I get an x squared value of 8.6 or so times 10 to the negative 7th. Now, x here is my OH minus, so this is my OH minus concentration. Okay, so if I take the negative log of this, all right, it is 8.6 times 10 to the negative 7th, and I take the log of it, I get a pH. All right. Oh, I get a pOH of 6.1. All right. So that means that 14 minus 6.1 is my pH, which is 7.9. And I'd expect my pH to be basic because this is a KB. It's slightly a basic, which it is. And it's a really bad base, so it's not going to be much higher than 7, which matches what I'd expect. Okay, so that's your equivalence point calculation. What I really care about the equivalence point, sure, it would be nice if you could do all these calculations for sure, but I want you to be able to look at it and tell me if it's going to be basic, acidic, or neutral. If you have a weak acid, your equivalence point is going to be basic. If you have a weak base that you're titrating, your equivalence point is going to be acidic. And if you have a strong ether, your equivalence point is going to be neutral. You should know that, and you should be able to write the equation for what is happening at the equivalence point. Okay? And then really the following calculations are just a simple KB from chapter 16. All right? The last thing that you need to do is in the excess base section. Okay? So this is region 4, excess base. Again, start with the same reaction. What's happening? This is the reaction that we're running, and it forms F minus and H2O. And I know I switched those around. I'm sorry. So we're still doing a before and after chart. So, like, what do I have? So I have 0.005 moles of HF. And let's say I'm adding 0.01 moles of OH, 0, 0. So what's left? 0 HF. And 0.005 F minus, OH minus, 0.005 F minus, and 0.005 H2O. Again, nobody cares about H2O. The change in pH due to the hydrolysis of F minus. So yeah, that's going to react with water, and it's going to form some hydroxide, but that is so small compared to this excess base. This is really the stuff that you care about that's dominating the pH. So all you have to do is calculate the concentration here. Again, your bar charts are moles. So you have to go back into concentration. How do you do that? 0.005 is your moles, and it's in how much liquid? Well, I added, maybe I have to calculate that because I didn't do that. So I have 50 milliliters of acid, right? And how much base did I add? Okay, so that's about 100 milliliters because it's like twice the amount. So let's do, there we go, plus, that's funny, plus 0.1. And this is how I get my moles of base. Not my total moles of base, not this, but my moles of excess base. What's still laying around that wasn't neutralized? I've overrun my acid at this point. I've neutralized all the acid and then added more base. So why did I put my calculator down? 0.005 divided by 0.15 gives me a concentration of 0.033. Okay, that's my concentration of OH minus. make sure you label those things, because when you're doing it with, and if you're doing a weak base with a strong acid, you're in the excess, right now you're in the excess acid section. So this would just be a straight, take the negative log of it and you'd get your pH. So just make sure that you are comfortable going in and out in either direction. Okay, so here I have 0.033. I'm going to take the log of that and I get a pOH of 1.48. So 14 minus 1.48 gives me a pH of 12.52. And that makes sense because I have a lot of excess base, so it should be really basic, and that is. Okay. This, again, would be different if you were doing a weak base with a strong acid, because here you would just have to calculate your excess acid, and you wouldn't have to do this step. Okay. But those are your titration calculations. You should know what a titration curve looks like. You should be able to tell what the pKa or the Ka of, or Kb for that matter, of an acid or a weak base is based on the curve using the half equivalence point. You should be able to tell me if the equivalence point is acidic or basic or neutral. And you should be able to calculate what volume they would be at various amounts, which is just the M1V1 equals M2V2 formula. All right? Good luck.